So, hello everyone. This is lecture 21 for the solid state physics. And in this lecture, we will start the free electron theory. Okay, but before that, I given you some work. Okay, so here I told you to calculate CV for the 2D and 1D, and also these factors like mu d, that is Debye frequency, Debye temperature, theta d, and Debye wave factor, kt, in 1D and 2D. Okay, so we already calculated in the 3D. We calculated all these factors theta d, mu d in the 3D. In 2D, what you have to do is nothing but you need to change this number of states, because this will be different for 2D, this will be different for 1D and 3D. Okay, so about this I talked in when we discussed the density of states. Okay, so for 3D we know the density of states can be found by this formula, L by 2 pi q 4 pi k square dk. And when you have this relation is for phonon. Okay, so it is for phonon. So from here you can see that d nu will be, we will write dk in terms of d nu, and dk will be this, and k will be, omega is nothing but 2 pi nu, so k will be 2 pi mu over vs. Okay, when you substitute the values, then you will get something like L cube and all. So this will turn out to be this formula, g nu d nu will be 3 into 4 pi, this v is nothing but volume, L cube vs cube mu square d nu. So we get this formula from here. We are just substituting the value of dk and k and L cube as v volume. So you will get this g nu d nu is equal to this for 3D. Similarly, if you need to calculate this for the 2D, then take this formula. Now substitute the value for k, that is the same. That will be 2 pi nu by k, 2 pi mu by vs. Substitute here and substitute the value of dk, then you will get something like L square and all. Let me show you here. After substituting the value of k and dk, you will get g nu d nu as this. So this will be the formula, and here L square can be replaced with a, that is area. Okay, so this will be the g nu d nu for the 2D, and for 3D you have this formula, for 2D you have this formula. And now just substituting the value of g nu d nu in this equation, where this is total internal energy, and we will integrate it from the 0 to mu d, that is Debye frequency. So you will get the all modes possible. So the energy of all modes will be given by just multiplying the energy of one mode, and this is the total energy. Then you will differentiate it with temperature, you will get the specific heat. So this will be the plan we're gonna follow. So let me just give you this for 2D. For 2D, we know that g nu d nu is this, means here for 2D we will multiply with 2 factor, as I told you before, and for 3D we multiply with 3 factor, because here 2 transversal and 1 longitude mode is possible, and 2D 1 transverse and 1 longitude is possible. So we will divide the speed in VL square and VT square, that is transverse longitudinal, and this is nothing but just the same formula. This is 4 pi a v by mu by vs square. Okay, so why it is 2 here? Because 2 will came out from here. When we take is vs, then it will be 2 by vs square, 2 2 4. So now it is here 1 by vl square, 1 by vt square, mu d nu. Okay, so we know that these number of states in 2D is nothing but 2 into number of particles, that will be 2 into Na for 1 mole. As 3 in 3D we take the 3 into Na. So from here you can find the value of this factor, and it will be mu square by 2, and value when we do substitute the limits, it will be mu d square by 2. So from here you can find this value, this will be 4 Na by mu d square, and substitute this here, means now we will write this will be the energy factor, and this, so in place of this we can write this, and mu d nu, and this is the average energy. I already given you this expression how we reach here. So just multiply and integrate. This will be just like same as we did in the 3D case. And here in the last you will get something like this type of integral. So it will be a constant value in terms of pi. So energy will be in the terms of, for the lower temperature, this limit will tend to infinity and 0 to infinity. This integral is given by some expression in pi, and that will be the constant. So you will get the energy in terms of t cube. So energy in the 3D case was in T4, and in the 2D case it is T cube. So when you differentiate it with respect to temperature, you will get T square here. T square here. So that CV is proportional to T square in 2D case. So that's what we needed to prove. Okay, means CV is proportional to T square in 2D. And similarly, when you do this same procedure for the 1D case using this equation, you will get this proportionality, that will be T. Okay, now when we need to find these factors, so how you can do that? So it will be same, means in the last you can solve it from here. When you return make them vs, so it will be again 4 pi a divided by vs square, that will be 4 na mu d square. So from here you can find the mu d, that will be mu d equal to mu s. Na divided by a will give you the number density per unit area, so that will be represented small n here, and this is 1 upon vs square. So vd square upon vs square will give this, and from here mu d can be calculated, it will be this. Okay, now we know that divide temperature is nothing but h mu d by k. So just substitute mu d here and you will get the expression for the divide temperature. And for the kd we know that 2 pi by lambda d, and lambda is nothing but v upon mu. So vs upon mu d. From here just substitute mu d here and you will get kd expression, and theta d we know already. Okay, so we calculated these for the 2D case. Similarly try to find for the 1D. Just procedure will be the same, and I already explained you these terms, the short tricks. So let's start with the new topic now, that is free electron theory. Okay, so what we will study in this, first we will see the introduction, what we see in this free electron theory and what is this. Then we will study the specific heat of matter in terms of electron concentration, Fermi energy, average energy, energy density, Fermi radius, Fermi momentum, Fermi velocity, Fermi temperature, then specific heat due to electrons. We see all these terms, what are they. Then we will go to the Drude model of electrical conductivity. Okay, then in that we will study the drift velocity, mobility, conductivity, etc. Then Mathias's rule and temperature dependence of resistivity we will study, and in it we also study the Lorentz formula. Then the Hall effect in metal and semiconductor in 2D and 3D case we will study. Okay, so this will take some time, this one, specific heat, all will be done in 1 or 2 lectures. Okay, means other than this will take a few lectures. So let's start without wasting any time. First let's see the introduction. What is free electron theory model? So this model is given by Drude and the Lorentz in the 1900. P. Drude and Lorentz theory. This was built to explain electrical conduction in metals, means how the conductivity occurs inside a metal. This theory explained that, and they take some assumptions. So what are those assumptions? First, the valence electron of metallic ions are free to move in the space between ions from one place to another place within the metal. Means the valence electrons, you already know what are they. So they are just free particles, or free particles we call them, and they will be free to move from one ion to another ion inside a metal. Okay, so if they are free to move, so we can just make an analogy which is similar to gaseous molecules. Like in the air we see that in a gas the particles are free to move anywhere, so we can just compare those electrons, free electrons, with the gaseous molecules. Therefore these electrons are called free electron gas. So inside a metal we call them free electron gas because they are totally free to move. These electrons also participate in electrical conduction. So these electrons are the main thing behind the conduction of electricity, also called conduction electron. So we call them the conduction electron. There is no, these are the assumptions, okay, what they take for the explaining this theory. So there is no interaction between these conduction electrons. So if we assume that there is no interaction between these free electrons, okay, that's why they are free. The interaction of free electrons with ions cores is negligible, means the attraction or pull or any coulombic force with the ions from the ions on the electrons will be negligible. So we consider them completely free. Now the free electrons find uniform electric field of positive ions. So they can be means they will feel the uniform electric field, means there will be no variations, okay, of positive ions. So we can take an example. Just take the example of sodium metal. So electronic configuration of sodium metal is nothing but 1s2, 2s2, 2p6, 3s1. So here we can see that in the outermost cell this is one valence electron. So if this sodium metal lose this electron, then it will be in a very stable state, okay. So that's why it wanna extract this electron and occupy the stable state. So this electron will work as the free electron. So if there is n atoms of sodium inside a metal, inside a sodium metal, then there will be n free electrons also, okay. So free electrons stay in the conduction band always, okay. So how can you find the concentration? There is some formulations of free electrons in the conduction band. So they will be equal to n for sodium metal, because there is only one valence electron contributed by the one atom. So if there are n atoms, then they will contribute the n electrons, okay. So a number density can be given by rho, that is n effective, means this is nothing but the number of electrons or number of atoms in a unit cell. You know how to calculate the net number of atoms in a unit cell, that depends on the unit structure, the structure of unit cell, okay. So that will be this multiply, this is molar mass, that is for 1 mole of gas, this is Avogadro number, this is volume of one unit cell, okay. So what you will see, this is if one atom, if n effective we know, then for the m mass we will get the mass of 1 mole. This is mass of 1 mole of gas, okay, gas or solid. Inside a solid, if we know the molar mass, then multiply with n effective, that will give us total mass of 1 mole. And this will be nothing but total volume, okay. Okay, understand it like this way. This m over Na gives you the mass of one atom. This is mass of 1 mole of gas, this is number of moles in 1 mole. So this will be give you the mass of one atom, and this is number of atoms effective inside the unit cell. So this will give you the mass of atoms in one unit cell, and divide by the volume of one unit cell, that is V. This will give you the density, okay, mass per unit volume. So just remember this. And this n effective can be changed, okay. It will depend on the what metal you are taking, okay. So for sodium it will be 1 here. So it can be written like this also, rho Na divided by m equal to n effective by V, okay. So this is nothing but atomic concentration, electronic concentration, this. So if we consider, this is for the sodium metal, because here only one electron is contributed by one atom, okay. If we take the example of magnesium, so the configuration will be 1s2, 2s2, 2p6, 3s2. So it will contribute 2 electrons per atom, so n effective will be 2 into n effective, okay, because per atom contribute this. So if there are n effective atoms, so they will contribute 2 into n effective, okay. So this is nothing but rho Na by m. So just remember this formula. Concentration N can be given by this. We call this concentration, number of electrons per unit volume. That will be the concentration N. So just remember this. Here rho is the mass density, mass per unit volume, and N is the number density, number per unit volume. Okay, so this will be given by 2 for the magnesium. Sodium, here it will be 1. Okay, if there is aluminium, that will give you 3 into N effective by V. So we can see that here. For aluminium metal, we have configuration this 1s2, 2s2, 2p6, 3s2, 3p1. There are 3 valence electrons, 2 plus 1, 3. So the electronic concentration will be 3 into N effective by V. Okay, so just remember this formula, and it will be equal to 3 into rho Na by m. Rho is the mass per unit volume density, and Na is the Avogadro number, m is molar mass, N effective in the number of atoms in one unit cell, and this is V. Okay, so this is just basic, very basic formula. If there are n atoms in a unit cell and every contribute 3, so N effective will contribute 3 into. Okay, in general we can write N equal to, this is nothing but the electron contributed by the one atom, that will be valency, and effective by V, this will be Z cut rho Na by m. Here Z cut is valency. This is for Z equal to 1 for Na, 2 for Mg, 3 for aluminium. So I hope you get this point. Now let's study some things. So in the previous lectures, in the Debye theory, Einstein theory, we studied about the specific heat of lattice for the insulators. Okay, so there we studied about the phonons and how they contribute. So we find this expression for the specific heat that will be in proportionality with T cube for the 3D case, and the graph is plotted by Debye temperature. If T is very less than theta D, then this will be follows, and when temperature is very higher, so it will just follow the classical law, and it will give us 3R. Okay, so in the lattice the heat is carried by phonons. So when heat is carried by phonons, then specific heat we can calculate. But in the case of metals, we see that the specific heat or the conductivity of heat and current is not just by the phonons but also by the electrons in the metals. So in metal there are 2 types of heat carriers, that are electrons and phonons. So Cv is nothing but contributed by electrons, specific heat due to electrons. C phonon, that is due to phonons. Okay, so we will see some things here now, that we already know this phonon term. We studied in detail in the previous lectures. Now we will study the electron, the specific heat due to electron. So electronic specific heat, if we see from the classical theory, then we consider this as the electron gas inside a metal, free electron gas. So we know that when a gas from the KTG, that is kinetic theory of gases, we know average energy of one particle in one dimension is nothing but 1 by 2 kT, that is from the equipartition law. So in 3 dimension we will have 3 by 2 kT per particle, so per electron. So this is for the per degree of freedom, and potential energy will be 0 because they are free electrons. So what will the average energy per particle? This is average energy per particle in 3 dimension, 3 by 2 kT. If we calculate the energy for 1 mole of solid, so there are n Avogadro number atoms, so just multiply it with the average energy of one particle, that will 3 by 2 Na kT. This will give you the R gas constant, so 3 by 2 RT, and from here you will calculate that C is nothing but 3 by 2 R. So according to classical theory, this specific heat should be came out to be this number, 3 by 2 R, and it will be constant according to the classical theory. It is not dependent on temperature, independent of temperature it is. Okay, but what we see experimentally, when we done experiments on the metals and we see the specific heat, then we get this graph. Means when the temperature is decreasing, we see that specific heat due to electrons, electronic specific heat starts to decrease, and with this formulation, that will be a linear curve like this, and we see that this never touches this value. 3 by 2r, never touches this value, this graph. And we can see that this difference is very much, means according to classical theory we should get this number, but we are getting this curve. So what we see that C is proportional to T according to experiments and not constant, and CE never becomes equal to 3 by 2r. This is experimental results. Now let's see if T equal to 300 Kelvin and CE classical will be this 3 by 2r and CE actual will be something, and this ratio came out to be 200. Means see that how much this classical one is greater than this actual one. Okay, so this can't be improvised. Okay, so now there is need to explain this curve, because according to classical theory this is not gonna give any results. Okay, so we are getting very wrong here. So where we are getting wrong, so let's see. So there are some theories given by some scientists. So there is this one theory, that is quantum theory, for this explanation of this curve. So what was there in quantum theory? It was electrons are treated as quantum particles, not as the classical particles. Okay, now we will consider them as quantum particles, not classical particles. And when we consider the quantum particles, then we know that electrons are fermions and they will obey the Pauli exclusion principle. What are fermions? Which have spin in fraction form. Okay. And what is Pauli exclusion principle? That two electrons cannot have the same all four quantum numbers. Okay, so if there is one energy state, so two electron can exist there but with the opposite spin. So two electron can't have same all four quantum numbers. That is Pauli exclusion principle, and which particles follow this are called fermions. Okay, and electrons are fermions. So now according to quantum theory we'll see how we can explain this. Before that, let me tell you something. Let's see, this is metal and these are energy states. Okay, now we will consider the quantum energy states because we are studying that, and they are continuous. Means I just shown them a little gap for the better understanding. Now let's assume temperature is 0 Kelvin. Okay, this is absolute temperature, that is 0 Kelvin. Now at that state we will see that there is this one energy level below which all states will be filled. All states will be filled. Okay, no electron will came out of this state, and this energy level at T equal to 0 Kelvin is called the Fermi level or the Fermi energy. And this is different for different metals, and if we take the average of all the metals, we will get that this energy nothing but approximately 5 electron volt. Okay, so this is called the Fermi level, defined as a level below which all states are filled and above all are empty at T equal to 0 Kelvin. So above this all will be empty, below this all will be filled at T equal to 0 Kelvin. We call this Fermi level. Hope you get this. Now let's see if we raise the temperature. What happens when we raise the temperature? So if T equal to 300 Kelvin, then we know that for the electrons we can calculate the energy. And temperature is, what is the definition of temperature? Temperature is nothing but the average kinetic energy of the particle, of free particle, that we call the energy. Okay, so this is the definition of temperature. Now E equal to kT, this will be the energy of one particle at particular temperature. So if we take the 300 Kelvin, then 300 into 1.23 into 10 to the power minus 23 something for boson constant, you will get this 26 milli electron volt. So what we did that if we raise the temperature 300 Kelvin, we are providing this much energy to the system. This much energy to the system. And this is nothing but raising temperature. So this is related with specific heat. Okay, electronic specific heat. Now what we see that in the classical theory, if we assume that, or it happens in the classical theory, when we apply some heat or we raise the temperature, then heat will be conducted by all the particles available. Means let's say this is the classical. Okay, so we this consider this electron gas, and when we apply this 26 milli electron volt from this, so this heat will be divided in all the particles. Okay, in all the particles. But this is not the case in the quantum states. In the quantum states, we know that if we apply 26 milli electron volt, so if we it will gain by this particles, then they can go nowhere, because to reach here they need 5 electron volts, but they didn't have this much energy. Even this can't go, this can't go, this can't go. Only the particles nearby this Fermi level can energize with this energy and can go to the upside, not all these particles. So this is the quantum theory, that not all the particles will receive this energy, only few particles nearby this Fermi level will occupy this energy. Okay, so this was given the quantum theory, but in the classical we say that any energy given will divide it in all the particles. So just keep this in mind, and let me give you some examples. If there are two boxes, okay, and here is 5 students, here is 10 students. Now you give 100 rupees and divide them equally in both of them. So this will get how much? 20 rupees per student. And here what you will get? 10 rupees per student. Okay, so number of particles is less than amount. If in place of rupees we provide heat, and inside students, in place of students we have particles, so every particle will receive more heat as compared to this, because this is divided in large number of particles. Okay, so you can understand, is this like specific heat? If we give some heat to this and some heat to this, which will be get it more heated? So this will get more heated, because this particle are less and each will receive more heat, and here each will receive low heat. Okay, so to raise the temperature of this system, the amount of heat will be less required as compared to this system. Okay, so that's why we will call that specific heat of this system will be less as compared to this system. Okay, so just apply it here. In the quantum state we have very small amount of particles which will receive the energy we provide, and here all will receive the energy. So to raise the temperature of this system we need more amount of heat as compared to this. Means same amount of heat can raise the temperature of this system more as compared to this. Okay, hope you get the point. So a large amount of heat is required to raise the temperature of this system by 1 degree as compared to this. We need very small amount of here heat. Okay, so specific heat of this system will be less as compared to this system. Okay, so this is nothing but quantum system, and this is our classical system. So this can explain this curve now. In the classical theory, here is the specific heat, means this amount of energy is required. Okay, this is very large as compared to the quantum state. Means if we consider the quantum state, it will define this curve. Means very less amount of energy is required initially. When the energy is more and more we provide energy, then more amount of particles below this will occupy energy, then more will occupy, then we see that with the increasing temperature the more amount of particles will be contribute to the specific heat, and the specific heat will start to increase with increase in temperature. So this explains this curve, this linear curve. Okay, and this will be always higher than this, and it will remain constant, because here all particles will receive whole energy all the time, but not here. Here the number of particles receive heat will increase with increase in temperature. So that's why we can say that the specific heat will increase with increase in temperature in the quantum states, but in classical theory it will remain constant, and this is not valid theory for classical one. That's why we accept this, because it is verified with experiments. Okay, and we also conclude that this never touches this value. So how we can explain this? Now let's see. This is the, if you need to achieve this one, then in the classical we know that all particles contribute, so these all particles should contribute to the specific heat. So for that we need this 5 electron volt amount of energy. Then we will say that this whole number of particles or electrons will contribute to the specific heat. So let's say energy given provided is 5 electron volt. So kT is equivalent to 5 electron volt. From here, when you calculate the temperature, it will came out to be 5 into 10 to the power 4. That is nothing but 50,000 Kelvin. So this is a very large amount of temperature which can't be provided on Earth. Okay, so this is means no metal can sustain this amount of temperature. That's why we say that this curve will never touch this value. Means these all amount of particles will never contribute to the specific heat. Okay, so if you didn't get this point what I just convey, just see this lecture again, and if you are still having any doubt, just put in the comment section, and you can try to contact me also through Telegram. Okay, so just let's stop here today. Tomorrow we will discuss this quantum theory more in the mathematical way. Okay, so just see you. Thank you.